All right, so this is section 11.5. Again, continuing on with our convergence and divergence testing, we're going to talk about what is called the alternating series test. Um, just to make sure we understand, the alternating series test will be a convergence test only. It will not tell you divergence. So if everything happens correctly and it passes the alternating series test, then you know that the series will be convergent. If not, it'll be an inconclusive test and we'll have to try something else. The good thing about the alternating series test is this is probably one of the easiest to recognize, okay, I need to try the alternating series test. And the reason for that is because for something to be an alternating series, the terms have to flip back and forth between positive and negative terms. And it's usually pretty easy to tell whether they're going to do that or not because you're usually going to have one of these terms like -1 to the n or -1 to the n plus 1 out in front in some form of your general term. It won't always be like that, but a large portion of the time, that's going to be the indicator that says, oh, okay, let's try the alternating series test. Obviously, if you're just given a list of terms and the terms flip back and forth between positive and negative, then you know alternating series. But again, if it's in its general form, the -1 to the n or the -1 to the n plus 1 or something similar to those is going to be the giveaway. So there's two conditions for the alternating series test. So first of all, and this is a little bit confusing the way it's written, a sub n in this top portion right here is considered to be the part without the -1 to the n part. I am used to calling a sub n the entire thing that you are taking the sum of, but in this case, they're separating that from that -1 part. Again, that's why it's a little bit confusing. Um, so here are your two conditions. The limit of the absolute value of the terms of the series, the a sub n part, have to be approaching 0. Okay, that really should make sense. Because if they're approaching anything other than 0, even if it is alternating, then you're just going to add infinitely larger numbers as you go. Whether they're positive or negative makes no difference. Um, and the absolute value of the a sub n plus 1 term has to be less than the absolute value of the a sub n term. Or in other words, if you take the absolute value of the series, they basically have to be decreasing. So let me show you what that means graphically. You might be thinking, well, yes, it makes sense. Some of you might be thinking, I don't get it. Let's take a look at it and see graphically what this is talking about. So if we just take a sub n as its own, and this is some kind of an alternating series, then what's going to happen is you're going to have a value up here, then you're going to have a value down here, then you're going to have one on top, down below, on top, below, top, below, and so on. Okay, your stuff, whoops, didn't mean to erase that. Um, that would be your alternating series. And what you can see there is that the alternating series is flipping back and forth in its terms, positive and negative, and then it's also getting closer and closer to 0 on each side of the x-axis in this case. So if you were to look at the absolute value of a sub n, well, everything that's already on top of the axis is going to stay exactly where it was. The absolute value of whatever that one was is going to be that term. That one would be there, that one would be there, that one would be there. But the ones on the bottom now, for example, this one, this one, this one, all these are negative. All it's going to do when you take the absolute value now is flip those things up. It's going to reflect them across the x-axis, and now you're going to have something that looks more like that. Whoops. And so on. And it's going to keep getting closer and closer and closer to the x-axis, but they're all going to be positive. Again, so now it looks like a decreasing function. So if one or both of these fail, then you can't use the alternating series test again for divergence. You'd have to try something else. You could go with an nth term test, or geometric, or whatever else you might be able to do. It probably won't be geometric, it'll still be alternating, but you get the idea. So hopefully that makes sense. Let's go ahead and take a look at some examples. So we want to determine the convergence or divergence of the given series. So you can see that alternating term out in the front there, the -1 to the n plus 1 times 1 over n. It's definitely an alternating series. So we have to test the criteria. So let's take a look at the limit as n goes to infinity of the absolute value of a sub n, which basically means let's get rid of that -1 term. Okay, that -1 to the n plus 1 is when you take the absolute value, basically it just goes away. So what we're really taking the limit of is 1 over n. And that definitely approaches 0. So that's the first criteria. The second criteria says if you take the absolute value of the a sub n plus 1 term, well, that has to be less than the absolute value of the a sub n term. And that has to be true. It does not have to be true for every term, but it has to be true for every term past a certain finite value. What that finite value is doesn't really matter, but your first, like, I don't know, 3, 4, 5, 6 terms, whatever it is, could alternate or do something crazy. But then after that, from there on out, it's got to be decreasing. So is that a true statement? Well, if you just look at the a sub n plus 1 term, that would be 1 over n plus 1, which is definitely less than 1 over n by virtue of the fact that the left side's denominator is always going to be bigger than the right side of that inequality. So that now is also a true statement. So we can say that a sub n, absolute value of a sub n is decreasing. So that is, we'll say for all n greater than or equal to 1, basically all n values here. So that is the second criteria. Therefore, a sub n is convergent. Or I guess in this case it would be actually the sum of a sub n. So that's where it differs a little bit from the other sections. I usually call the whole sum a sub n, but they're really just referring to the part that you're taking the sum of here. All right. Second example. Determine the convergence or divergence of, again, you can see that you've got the sum of an alternating series, so it's -1 to the n plus 1, and then we've got n plus 1 over n. So you could try starting with the alternating series test here, but when we do, you get the limit of the absolute value of a sub n, which is going to be n plus 1 over n. Well, that limit is 1. Okay, that is not 0. So this is inconclusive by using the alternating series test. So we have to try something else. So let's just try taking the limit straight up. Let's try the nth term test for divergence by taking the actual limit of this. Well, the problem with this is if you take the limit including the -1 to the n plus 1 term, you don't know what this thing is going to approach. It's either going to approach 1 or it's going to approach -1. It's going to basically keep bouncing back and forth. And because that's what happens, this limit does not exist. And since the limit here does not exist with using the nth term test for divergence, this one is divergent. Remember, the nth term test for divergence, anything other than 0 for your limit means that the series is divergent. So this is what's really happening on this one graphically. What we've got is whatever this thing starts off as. If you were, like, let's say you plug in a 1, if you plug in a 1 here, you're going to get, what is that, 2 over 1, 2? So yeah, you get a 2. And then you'll get a number down here, which would be negative, and then a positive, and then a negative, and a positive. And it looks like it's doing this correctly, but what's going to happen is these things are going to start to level themselves off and approach 1 and negative 1 respectively, and they will never approach 0. So in that case, this is going to be a divergent series. You cannot add that sum up. But again, it would not tell you that just by using the alternating series. We had to go with the nth term test for divergence after we realized the alternating series test criteria failed. All right, example number 3. Convergence or divergence of the series negative 1 to the n, natural log of n minus 2 divided by n minus 2. So we can see it's alternating. Let's try the criteria. The limit as n goes to infinity, we'll do this of the absolute value, which is going to remove the negative 1 to the n part. So we're going to take the limit of the natural log of n minus 2 over n minus 2. And substituting in infinitely large numbers here, the numerator and the denominator both approach infinity. So we can use L'Hopital's rule here, which now says that I can take the derivative of the numerator and the denominator. And the derivative of the numerator is going to be 1 over n minus 2. And the derivative of the denominator is 1. So really the 1 part there in the denominator is unremarkable for us. So we're going to have the limit as n goes to infinity of 1 over n minus 2, which does go to 0. So the first criteria is met. The second one is not as easy to see. You have to show that the absolute value of the n minus 1 term is always going to be less than or equal to, less than the absolute value of the n term. The problem with this is both the natural log and the denominator, which is linear, are growing. So how can we show that this is always a decreasing function when you take the absolute value? Well, we can change it into a function of x. Call this the natural log of x minus 2 over x minus 2. And if you want to show something is decreasing for certain values of x, you're going to take a derivative. We're going to find the slopes. Slopes tell you positive increasing, negative decreasing. So take the derivative. It is a quotient rule. The derivative of the numerator is 1 over x minus 2 times your denominator, which is x minus 2, minus derivative of the denominator, which is 1, times the numerator, which is the natural log of x minus 2, all over the denominator squared. Okay, in order for us to show that this is decreasing for certain values of x, we need to make sure that this derivative is less than 0. All right, well, the denominator, for every value of x that you substitute, other than 2, because 2 is undefined, but it's okay because n here starts at 3, and that was kind of important. For every value after 2, the denominator is always positive because you're squaring it. So we don't really have to worry about that. We can multiply both sides by the denominator, get rid of it, whatever. On the numerator, 1 over x minus 2 times x minus 2 is 1. And then I've got minus 1 natural log of x minus 2, and that has to be less than 0, multiplying the denominator out of there. So now we need to solve this for x. So we can add the natural log of x minus 2 to both sides, and then to get the x out of the natural log of x minus 2, we can exponentiate both sides. And when I do that, exponentiating Exponentiating the left just gives me e. Exponentiating the right gives us x minus 2. And then we can add 2. So we get e plus 2 is less than x, or another way to say that is x has to be bigger than e plus 2. Well, again, e is about 2.71 or so, so that means that x has to be bigger than, I don't even know how you do bigger approximately. Never thought about that before. But let's just change it this way. So we know that e plus 2 is going to be approximately 4.72, and the x here is representing our n values, and since n are only whole numbers, n has to be greater than 4, or you could say greater than or equal to 5. But that means for every n value greater than or equal to 5, this is going to be a decreasing function. So that meets the second criteria. Therefore, this one is convergent. Okay, it's a lot of work to do when you have to prove the decreasing portion of this. You might have to take a derivative to show all this information. All right. Let's see, the convergence or divergence. -1 to the n shows alternating. If we want to look at this one's limit, it definitely appears it's going to fail the first test. The limit as n goes to infinity of the absolute value of this portion will give us 3 to the n over n plus 1 squared. And since the numerator is exponential, the denominator is a polynomial, the numerator will grow faster than the polynomial. So that limit goes to infinity, which means it is inconclusive and it fails. So let's try the limit of the actual function itself, including the alternating term. Well, if you think about it, since the absolute value term went to infinity, if you include an alternating term, it's going to kind of start to bounce back and forth between positive and negative infinity. So in this case, you know that this is definitely going to be a does not exist, which is going to indicate divergent. And again, real quick, just to kind of show you what this is doing graphically, you can actually plug this into your calculator if you want to see it, if you know how to do that. But basically, what's happening is something like this. On both sides, it's starting to spread itself and go towards positive and negative infinity as n gets bigger and bigger. So that's kind of what's happening there. All right, I think that is enough for this video. We will come back and finish up examples 5 through 7, and then we're going to talk about the alternating series estimation theorem.